So in this last video from 3.5, we're going to talk a bit more about binary search trees. So now that we've looked at lists and recursive functions, let's look at how we might apply recursive functions to trees. So we've done this a little bit before. We defined a recursive relation for the number of vertices on a binary search tree, but we're going to do something slightly different here. So recall from section 2.1.2.6 that a binary search tree is a binary tree where the left child of a vertex is less than the vertex it came from, and the right child is greater than that vertex. So in our example, we used words. If we were to use words, the word coming first alphabetically would be considered less than and go to the left, and a word that comes after alphabetically would go to the right. So let's define kind of a recursive definition in the following way. Let T be a binary search tree. We're going to define the function in order of T as follows. If T is the empty tree, then in order T is going to output essentially the empty listing. It says the empty list. And if T is a single vertex, then in order T is just going to give essentially that vertex R. So those are kind of our two base cases, our two simplest options. And then our recursive case is going to be if T has a root and subtrees, T sub 1 and T sub 2, then the function in order T is going to give essentially the list in order T sub 1, comma R, comma, in order T sub 2. So it's essentially taking the two subtrees and kind of sandwiching them around the root. So the commas are going to be part of the listing. Remember from a couple videos back that the commas are very important in the list. So here's how we're going to use this function. And we're not going to prove that this one works. We're going to kind of take it for granted here, but let's see how it would work. So use the definition of in order function to print the list of words in a binary search tree from the example 4 of section 2.1.2.6. So I've written it out here. Your notes don't have it written down yet, so if you need to take a second, go ahead and pause the video and write that down really quick. But we looked at this example in 2.1.2.6 where we essentially put these words into the binary search tree. And we were looking at it in terms of like a dictionary from like a word processing system. So we want to go ahead and we want to use the in order function, if you will, for this tree. So we're going to name the entire tree T. So if we have in order of this entire tree, now notice that this tree is essentially made up of two subtrees to begin with. So we have a subtree here and a subtree here. So we essentially have a T sub 1 and a T sub 2. So if we use our recursive piece of the definition we looked at before, in order T is going to give us in order of the T sub 1 subtree, comma, that root that it came from. So the R in the recursive case here is going to be this muggle. And then in order T sub 2. Well, now we essentially have to take care of the in order T sub 1 and in order T sub 2. So let's take them one at a time. So let's look at in order T sub 1 first. So if we look at kind of the tree T sub 1, we kind of have a root that's Fleek, and then it does kind of actually have two subtrees, if you will. It's just that one of them is empty. Okay, so we do have kind of an empty piece off to the side here, and let's go ahead and name these. Let's do T sub 1 and then a 1 up as well, and then T sub 1 with a superscript of 2. So if we were to do this using our recursive piece on just in order T1, we'll take care of the rest later. This would essentially become in order T sub 1 superscript 1, comma Fleek, comma, in order T sub 1 superscript 2, and then the rest would just follow for now, muggle, and the in order T sub 2. Well, now we have kind of these two simplest cases, this in order T sub 1 superscript 1 and the in order T sub 1 2. Can I just call them T1 and T1 2? So this kind of goes back to our base cases of the definition. So in order T1 1 is a single vertex. It's just fantabulous. So in order T11 would become fantabulous. Fleek would stay fleek. And now in order T12, since that was empty, this would give us the empty string. So we don't like leave a space for it at all. It's just kind of, it squishes itself back together. So we are left with essentially nothing from the in order T12. So then we go straight to muggle and then in order T sub 2. So now we have to take care of the in order T sub 2. Well, if we go over to T sub 2, well, this again is also made up of technically two subtrees. We've got Smushables and Wurfing. So let me name these T21 and T22, if you will. So if we go ahead and use our recursive definition for our function here on in order T sub 2, so the front pieces are all going to stay the same, and let me shift it over a little bit so I can fit them all. So Fantabulous, Fleek, and Muggle are just going to come along for the ride. And then the in order function tells us that we essentially take the two subtrees, Smushable and Wurfing, but we're going to call them T21 and T22 for now. And we're going to essentially sandwich them around the root of Snizzle. So we'll have in order T21 Snizzle and in order T22. And now the last thing we essentially have to take care of is the in order T21 and the in order T22. Now those are essentially the base case 2 because they're both single vertices in each case, in each subtree. So they're just going to become that vertex. So essentially we have Fantabulous, Fleek, Muggle. In order T21 is going to become Smushables. Then Snizzle comes down, and then in order T22 would be Wurfing. So essentially what this essentially ends up doing is it essentially ends up listing them in alphabetical order. And that's how that definition would work on this binary search tree. So that's going to be the end of this video. This is the end of section 3.5.